Hi everyone, how's it going? Yeah, doing good. Cool. So last week, we started getting into ML ops. Assignment 10 is almost ready. I'm so sorry, everybody. Assignment 10 is basically you're going to do ML flow like end to end. So hopefully ML flow will help you a lot with your group project. So it's not going to be due until the end of the semester. Both assignment 10 and assignment 11. Those will be due at the very, very end. So you can take your time with them, play around with things. So assignment 10 is about like training model registries, right? We talked about that a lot last week. Um, kind of preserving artifacts that they're available in other places. And then the next bit will be the inference bit, right? So then how do you actually end up serving that? So with ML Flow, what we're going to do is we're going to deploy it locally. Whew, there's markers this time. All right, great. We're going to deploy it locally. Just, play around with it. Then you'll deploy the ML Flow server in the cloud. You'll use a Spaces bucket as your actual registry, and then you'll use a PostgreSQL database as your backend for logging all the metadata, things like that. So then you'll piece everything together. So you'll get a little bit of experience. How do we have all of these different parts talking to each other? So hopefully that'll be fun. And the next bit will be inference. So yeah, so moving on. Today we're talking about LLMs and LLM ops because it's not enough to have ML ops. We have to have LLM ops. You'll see why it actually makes sense that these are kind of like, I mean, they're related disciplines, but there's enough architectural stuff going on that I think it makes sense to like have these, think about these separately. So in order to get into LLM ops, I think we need to understand a lot about LLMs and how they operate. We need to talk about retrieval augmented generation. We need to talk about agents, all of these things. So this lecture is going to be kind of like the highest level overview of this space. We're gonna and just as like a level set, because in case you haven't gotten the opportunity to sit down with LLMs and kind of understand what's happening, we're gonna go over transformers, transformer architectures, self-attention, things like that, again, at the highest level possible. There are no equations in these slides. So, but if you are interested in it, let me know. I'd be happy to provide more resources for you. And also, there's people in this room who know way more about LLMs than I do. So if I get something wrong, please call it in, just like, nah, that's not quite right. I did my best though. It's the latest and greatest, up to date, supplemented with information from KubeCon. So, all right. Large language models broadly are we want to start with like the task that they were designed to do. And that task is next token prediction. So given some set of text, some prefix of text, the language model assigns probabilities to subsequent words to then return those words, right? So if we say, if the prefix of a text is the most famous city in the US is, there's going to be, if you train your language model correctly, uh, New York and Los Angeles will have higher probability than, for example, Sharpie and laptop as the returned results, right? So that's in a nutshell what we're doing with large language models. That's what they're designed to do. So we're going to talk about how we get there. So the way that language models have come to fruition is through transformers. So a transformer architecture. So transformers are a neural network. And I don't know if in your machine learning class you have gotten into neural networks just yet a little bit. Yeah, cool. So it's a type of neural network that's going to process a sequence of tokens in parallel. And have we done a little bit of NLP or just a tiny bit? Everyone? Yeah. So we know when I say token, we know what we're talking. Okay. Yes. Okay, cool. So great. So it's going to process a sequence of tokens in parallel. And specifically the key innovation that brought us large language models as we know them today is something called a self-attention mechanism. And we'll talk a little bit more about that. Essentially, before we had attention mechanisms, we were using recurrent neural networks or RNNs to process like long sequences of text. There's a lot of issues with that. It can be really slow to train. And what would happen often was a vanishing gradient problem. So as you kind of go further and further into a text, you start remembering less and less information. So then we had LSTMs, but anyway, moving on. There were some issues with some of the ways we were processing sequences before we had self-attention mechanisms. So what we're going to do, the input for our language model is going to be, some string of text. So say we're doing a translation problem. Our string of text is going to enter in as just French tokens, right? So just individual French words. And then what we have to do is we have to represent those as embeddings. And then from there, we do all these kinds of transformations. We're going to get another set of embeddings that we call our output embeddings. And from that, we can generate the output text. So we all feel okay about embeddings, yes? Okay, cool. Great. I wasn't sure like what level to put this material at. Okay, so to prepare our input, we had to do a couple of standard things. It sounds like everyone's pretty familiar with this. We need to do like text normalization, maybe like case folding, things like that. We need to do our tokenization. So that could be on words, that could be on subwords. BERT operates sometimes on subwords, which is really, really helpful. And then once we have those individual tokens, we're going to map them to a series of IDs, right? So we'll have our vocabulary, and then those will all be tokens. And then we have over here like a dictionary of like, ID1 goes to the word je, and ID2 goes to the word suis, and then ID3 goes to the word whatever. I almost said estudiante, but that's Spanish and not French. I don't know any French. Anyway, but yeah, so you end up mapping those. So you have an ID for each word in your vocabulary or each subword, or each character, depends on what you're tokenizing. And then what you get is, as a result of that, there's other ways to create these, but you ultimately you're going to end up with an input embedding that's just a high dimensional vector that represents the meaning of each token in the sentence. So we have our tokens, and then from there we're going to go to our embeddings, and the way we generate those embeddings can be a lot of different ways, a lot of different models and methods. I don't get into all the different embedding techniques in this lecture because I feel like that's kind of outside the scope of it. You're just going to choose a model to do your embeddings. Maybe that's you could do something as simple as skipgram or bag of words or continuous bag of words or word2vec or whatever you want to do, right? BERT, but you're going to translate these tokens into embeddings. And then, yeah, and then you're also going to add a positional encoding, right? So that positional encoding could be explicit or it could be implicit, right? So it could just be like its placement in a feature vector. That could be an implicit positional encoding, or you could have an explicit, like you append some vector to your feature matrix in order to indicate that's where it is in the vocabulary. Okay, so self-attention. I've been working with attention mechanisms for like 4 years now, and sometimes I'm still like, do I really know how this works? Like, am I sure? I've even implemented like additive attention from scratch because Keras stopped supporting additive attention. I needed it for a model, so I built it from scratch, and I'm still not totally sure that I know how attention mechanisms work. So if this feels like a what is happening kind of situation, that's okay. Just use Keras. So your self-attention mechanism is going to help determine the relationships between different words and phrases in some input text. So for example, if you have, some sentence like, the cat sat on its, I almost put apostrophe, pause, right? We want to, our attention mechanism is going to help us understand that, it's and cat and pause are probably a little bit more related than, maybe like sat and I don't know, maybe let's add sat on his paws on the couch, right? So maybe sat and couch are going to be a little bit more related than cat and paws or cat and its, right? So the way that we get to that kind of natural language understanding or that contextual understanding is by doing something called a self-attention mechanism, by using an attention mechanism. So what we're going to do is each input embedding is going to be multiplied by 3 learned weight matrices, right? So each word is going to be tokenized, and then we're going to have some high dimensional embedding that's going, or some high dimensional vector that represents each word, right? So this would be our feature matrix. So it'd be dimension 1 is always this way, and then dimension 2 is that way, right? So it'd be like 9 by 300, say if we use like word2vec. And so each of these is going to be multiplied by some learned weight matrices, and it's going to generate they're going to be our query, key, and value vectors. So the query is the vector that helps the model ask like, which of the other words in the sequence are relevant to me, right? So if we have a query, that's going to be like, let's say, sorry, cat. the query vector is going to be like, okay, of all of these words, which one is the most relevant to cat? And then it kind of keeps going, right? Then our key vector is going to be, it's like a label that we have that's going to help the model identify how a word might be relevant to other words in the sentence. So if this were a translation task, we would have, the same thing in French. Again, I don't know French, but yeah, you would be able to say, okay, great, this is labeled. So we have this, the cat sat on his paws on the couch, and then the French translation, and then the key is going to help like identify like which of those words go together for that translation task. And then the value vector is going to hold the actual word content information. So this is very in the weeds. Like never going to test you on like, what's the query key and value? Just like giving super high level. There's nothing on that slide. I'm sorry. Okay. So what we're going to do is we are going to calculate scores once we have these vectors. We're going to take the dot product of the query vector of one word with the key vectors of all of the words in the sequence, right? So we have query, and we're going to take the dot product with all the other vectors in that sequence. Then we're going to normalize just by some typical normalization techniques. We're going to divide that by the square root of the vector dimension. And then we're ultimately going to end up with these weighted values. That's the key thing of all of this, right? So it's like, it's 3 vectors. We end up like doing some multiplication, some normalization, and then the output is going to be these weights, and that's going to be our attention weight. So the attention weight is going to be this like context-aware representation for each word. So key point being here is that we can say, all right, so of all of these words, our context vector for our attention weight vector rather for cat, as pertains to pause and as pertains to its, those weights are going to be more, those are going to be more strongly weighted with each other because that's going to help represent that those are more related. And then sat and couch are going to have higher weights with each other, and that will represent that they're more related. So just the key bit is like it helps you just map which words in a sequence, which tokens in a sequence belong together more closely. That's pretty much it. That's what we're looking at. Then we have multi-head attention, which actually I'm going to skip over that. Let's just get into encoder and decoders. So all of this to say, so what we're doing here is we are taking an input sequence of text, and then we're doing some transformation on it. Self-attention is like a fancy transformation that we're doing. Multi-head attention is an even fancier transformation. But basically, we have this encoder and decoder architecture. And I'm talking about these because when we get into the different kinds of LLMs, this is really important for knowing how to operationalize each kind of LLM because they have different architectures, right? So when we have an encoder and let's just start with the encoder. The encoder's primary function is just to process some input sequence into some continuous representation that's going to hold contextual information for each token. So have we played with convolutional neural networks before? A little bit? No? So convolutional networks, yeah, I like using that as an example because it kind of shows you like how things get smoothed out in a certain context. So if we have a convolutional net, all right, so say we have a convolutional window of 2. What we're going to do is move over, let me add one more. 2, and then 2. We're going to take this window size, which is 2, and then we're going to do some transformation on these values. Then we'll do some transformation on these values, another transformation on these values, and then the resulting vector is going to be kind of like a way of aggregating across this whole vector, right? So if these were individual words, say these were each vector of length 300, right? Then when we're doing a convolutional network over them, then we're going to have like this really nice way of representing like how these go together, right? So with encoders, that's kind of what we're doing. We're taking our input vectors and we're doing some transformations going to help understand the context that vector exists in. So again, we're going to normalize our input sequence, all the standard things, tokenization, converting them into embeddings, and then we'll create those positional encodings to retain the sequence information order. We can use the self-attention mechanism after that to then like each token in the sequence can be dynamically attended to with every other token, right? So here's a vector 300, right? So it's going to be tended to with every other token to best capture the relationship of these words to each other. And then the output of that encoding step is going to be another series of embedding vectors in some vector space Z, let's call it, representing the entire input sequence, right? So then now we have our whole input, and then once we have our encoding step, this entire sequence is going to be represented by some other vector space called Z. I don't like that I called it Z because Z stands for the integer space, but that's okay. I'll fix that in post. All right. So now our decoder. Our decoder is going to take that out the sequence that our encoder generated, and then it's going to do some other transformations, get something back out of it, right? So that's again going to work token by token. And then our decoder layer is going to have one of two types of attention mechanisms. Either we can do like a masked self-attention, where basically each position can only attend to earlier positions in the output sequence. So if we were doing a translation task, then if we're working on position 1, the rest of the sentence is going to be masked for the decoder, right? It's trying to predict what the next word is. If the token that we're on is cat, then this bit is masked and it's going to try to predict that next bit, right? So that's masked self-attention. And then we have cross attention. So that's going to let the decoder focus on only the relevant parts of the input sequence using the embeddings generated from the encoder. So yeah, and that's just going to continue until we have like an end of sequence tag. And we know about our positional tags, end of sequence tag, beginning of sequence tag. Yeah, okay, great. All right, so a lot of the recent LLMs that are out are a decoder-only transformer architecture. So that means that we're not really adding in a bunch of extra fancy stuff for our encoding layer. We're really just working with the decoder-only architecture. So that means it's going to focus a lot on directly generating the output sequence from an input, right? So the input sequence processing is still going to include the embedding and the positional encoding, but it's not going to add a bunch of extra stuff. You're not going to have like a million other like, feed forward networks or whatever self-attention mechanisms on the input. The real task and the challenge is to just generate the output. So it's the masked self-attention mechanism that helps the decoder learn what's the next sequence should be. Does that start to make a little bit of sense? Yeah? Okay, cool. So when we are training our transformer, we're just modifying the parameters of the model, which I think is clear to this group. And then when we're doing inference, what we're doing is we're only using the predicted output, right? The inference step is like our predictions. And we're not updating our model weights at inference time. The model parameters are fixed during inference, right? So that seems a little bit strange because we keep hearing about things like retrieval augmented generation. But if our model parameters are fixed, how do we start to incorporate additional data, right, into our model? That seems like a challenge. We'll get there. So let's see. I think everyone's probably okay with that. Okay, so let's talk about some of these different architectures. So we have our decoder only architecture. That's going to be pre-trained on our language modeling task, right? So our next sequence prediction, our masked attention. So the target sequence for a decoder is going to be the shifted version of the input sequence, right? So the cat sat on, oh, sorry. Let me have parity with my slides. So the cat sat on B would be the next target, right, of this. And then if we move it over one more, the cat sat on B, then the next target is Matt. Does that make sense? Yeah, okay, great. I heard one, and then I was like, yeah, great, everyone understands. Are we in a good spot with this so far? Yeah, okay, cool. We also have encoder only transformers. So a very famous one is BERT. So bidirectional encoding recurrent, what is it? Sorry. What is the BERT acronym? Bidirectional encoding representation transformer. Yeah? Recurrent transformer? Bidirectional Sorry, can someone Google that for me? Appreciate you. Thank you. Thank you. Thank you. All right. So BERT is also a pre-trained model, right? So if anyone's ever used BERT, you can just grab the entire embedding space from BERT. And it's the way that it's trained is it's basically corrupts the input sequence and has the model try to reconstruct it. So it helps you kind of move down as you're moving down your tokens. It corrupts some like the input, and then the task is to recreate the output, even though there's perturbations. And so that's another like mass language model. So in this case, right, so we have the mask set on the mat, and what we want to output is the cat set on the mat, right? So that way we have another like masked attention mechanism situation going on, but it's at the encoding side. And then we have encoder decoder, right? So you encode your stuff and you decode it coming out. So we use encoder decoder a lot for neural machine translation, right? So from French to English, we use it for question answering. We use it for text summarization. A lot of different tasks are kind of born out of this encoder decoder architecture. And if you'd like to know how we set up our training data for that, I'm happy to go into more depth on that. Oops. Okay, so next, let's get into context length. So the context length is just the number of tokens that that model can remember and then use to predict the next token in the sequence. So when we had just RNNs and LSTMs for this, this did not perform very well. We had, we had a very, very short context window when we were working with RNNs. Now we can have massive context windows, right? You can feed, an entire PDF to whatever model and have it summarize it for you, right? The longer the context length, it's going to allow the model to capture more complex relationships between text in that document, and then also like dependencies within the text. So overall, the key takeaway there is like the larger your context length, the overall like the better the output is going to be. But being able to handle those longer contexts requires a lot more computational resources and memory. So when you are handing a massive document to a model to summarize, the amount of compute and memory required to then return a summary is much higher. And so we are always going to have this balance between performance and training, right? That sounds sensible. If you had unlimited resources, you could just train forever and just have the most amazing model ever. So that's one of the reasons that a lot of these foundation models come from very, very wealthy companies, right? They can afford to train on many, 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 many GPUs for a month. So, that's part of the centralization of it. So let's talk through how transformers evolved in the last 6 years or so. GPT-1 came out in 2018, yes, I think, pretty sure. And this is like the first, so GPT stands for Generative Pre-trained Transformer. So GPT-1 is Generative Pre-trained Transformer version 1. And so that was a decoder-only model developed by OpenAI. And the data set that it trained on originally was only like a couple billion words. Doesn't that seem so quaint? It's so cute. But there were some really key innovations that happened as a result of GPT-1. It combined transformers and unsupervised pre-training. And so this kind of like semi-supervised approach to training, basically, so there's unsupervised pre-training, and then that was followed by a series of supervised training steps. So semi-supervised training kind of started to take over some of the scene, I guess, in NLP back in 2018. So that was really interesting bit of AI history. So the task that GPT-1 was trained to perform was next token prediction. And so it wanted to do task-aware input transformations. And so question answering is going to require a document. And the document in NLP land, we call that just like we call the question a document. And then the set of documents that it can match with are called the queries. So basically you have a question and a bunch of answers that you can have. And then GPT-1 kind of converted that task into a different task. So it converted it into structured inputs that the language model can then parse without requiring that task specific setup, right? Has anyone played with question answering preparation, like data preparation before? No? Okay. It's very similar to like information, well, question answering is a subset of information retrieval. But it's very similar to the way that we set up information retrieval tasks. So the way that we do it is like these. We're gonna have like our document and our queries, which is strange terminology, I know. That's just like, maybe it's like old school, like we talked before, we're using queries in the ChatGPT style. But like if our document was like, what is the best class in MIS? Then the answers could be, 531 and 5, what is this class? 47. Thank you. 545. Cool. So with question answering, you have like your, obviously this is subjective and not objective, but imagine this were an objective question. With question answering, what you can do is you have like your one document and then you serve it, as many answers as you might want to. And then you have your labels, right? So a lot of it would be like supervised learning. So you'll have some labels. And so you can also set this up as like a ranking task. So usually those are the metrics that we use. Information retrieval or ranking metrics. So then we have like our rank. And then we want to say like, okay, well, clearly 547 is the best one, right? So that's going to have our label. And then you can set this up with like, you can either do it as a binary sort of, what would that be? Yeah, if you set it up as a binary, so this is the correct answer and these are incorrect answers, you use one set of metrics. You can also set up as ranking task properly. So you could do 1, 2, 3, right? Was that correct? Did I get it? No. Okay. Anyway, that's fine. And then you feed this whole thing into your model, right? So the really interesting thing about GPT-1 was it did not need to be fed data in this format, right? It was able to, I have my own philosophical ideas about this, but the hype was that it's able to do this question answering data input without having to explicitly be fed this ranking task. I'd argue that, you have high enough context with all of your massive embedding space. It's not that you're actually doing question answering, you're just doing very effective next token prediction is my hot take on it. People disagree with that. Okay, so that was one of the key things there. BERT. Yeah, we talked about BERT already. So that was like the next hotness was BERT. BERT actually came after GPT-1, which I think is interesting. That's not how that is organized in my brain. But BERT actually came out in late 2018 or like early 2019. BERT was the encoder only architecture, right? So as a result of BERT, you get these like really, really, really high quality pre-trained vectors that you can use and then just basically you just query, right? So it's like if I wanted to represent V in like BERT speak, I just pull down the BERT model and then I look up the vector that represents V and there I have it. You can do some other kinds of, you can like customize it. So there's a character BERT, there's sentence BERT, there's sequence BERT, there's whatever BERT you want. If you want more context about that, you can feel free to read through the slides. Then we have GPT-2 in 2019. And basically the difference between GPT-1 and GPT-2 is just an order of magnitude more data. So in this case, they trained on about 45 million web pages from Reddit that had karma greater than 3. Maybe everyone here is too young to use Reddit. But like with Reddit, like karma is like an upvote, basically. It's an algorithm of upvotes to downvotes. Yeah, so about 40 gigs of data. And it's up with 1.5 billion parameters, which sounds like quite a lot, doesn't it? And that is many, many, many parameters internal to that model. And it performed really well in some tasks, but it didn't outperform state-of-the-art, like in reading comprehension, in text summarization, in like even in machine translation, which I think is interesting. But the most significant achievement was that it did zero-shot learning on a variety of tasks. So basically, that's zero-shot learning is the ability of a model to generalize to a new task without being trained on that task explicitly. So for example, if we had an input, which was just like some English sentence, and then we had comma, and then just pass it the English word German, and then prompt it, right? It would just intuitively know to translate that to German. Is that zero-shot transfer learning, or is that actually just, again, like very high probabilities if you had this English, you know, like an English sentence, and you're like, and now German, right? Maybe Reddit has been like, hey, how do I translate this into German? Anyway, and then someone responds. Anyway, that's maybe in the weeds. I think it matters, you know, tasks are important. I don't know. I'm not ChatGPT-2. I'm not GPT-2, and I can't see inside its brain. But yeah, so next up, we have GPT-3 and 3.5. And the most notable difference was just the size, right? So GPT-2 had 1.5 billion parameters. GPT-3 has 175 billion parameters. That's a lot. That's a lot, y'all. So it's able to store and recall huge amounts of information. It's able to generate more coherent responses to prompts. And then it just generalized better across a range of tasks. Generalized better across a range of tasks. Okay, I've made my point. I'm going to shut up about it. So one of the key things about GPT-3 is that it used instruction tuning for the first time. So we have something called Instruct GPT. So basically, that's just reinforcement learning from human feedback, which is how we start to get into this blend of like, okay, well, we have this model, this like massive model that has 175 billion parameters. It still doesn't do exactly what we want it to. So let's start adding some pieces on top of it, right? So let's start like interacting with it a little bit more, adding maybe some tooling, adding some other data that we can use to augment it for certain things, right? So that's where this like new flavor of stuff starts to emerge. We're not just relying solely on one model to do the thing that we want it to do. And maybe if we just make it bigger and bigger and bigger and bigger and bigger, it'll solve all of our problems. Now we're starting to get into that space of like, maybe we need to adapt some external tools or tools external to the model to improve it. So reinforcement learning from human feedback. There's Instruct GPT only had 1.3 billion parameters, but it had better human evaluations than the vanilla GPT-3 model. So that was like, yeah, using some human feedback to basically take this massive GPT-3 model and then like condense it through reinforcement learning into 1.3 billion parameters, right? And then we have GPT-4, and like, you know, we've all played around with this. It's GPT-4 is multimodal. I think is one of the key differences, which is really cool. So it can process image and text inputs and then produce text outputs. So GPT-4 does not do image to image. It's not doing text to image. We have other things for that. We've got Midjourney. What else? Wait, what was it? Dolly. Dolly. Yes, thank you. Yeah, stable diffusion. Yes, exactly. So GPT-4 receives a context window of up to 128,000 tokens. Yay, so you can feed it 128,000 words at a time, and it'll still perform, which is nuts. Yeah, the maximum output right now ish is around 4,000 tokens. And it can also start to approximate achieving complex tasks like mathematics, coding, right? Generating code, machine vision. It can start to approximate performing well with like law documents and psychology documents, things like that. So yeah, and that's without RAG on top of it. It's vanilla GPT-4. Okay. We have some more models that we'll go through. It's just that the architectures matter, right? So we have a Lambda, which is language model for dialogue applications. That's designed for open-ended conversations, right? So dialogue-focused data, back and forths. And that it's its primary focus is maintaining and enhancing conversational depth and breadth, right? So if you are like a school enrollment advisory chatbot or something, maybe you want to use something like Lambda and then use some RAG on top of it. You might have better performance using that than you would with like just like using the OpenAI ChatGPT-4 API, right? Like the different models they do different flavors of things. There's Gopher. Gopher has 280 billion parameters, and that's a decoder-only architecture. This was DeepMind's model from 2021. Again, text generation, language translation, all the usual suspects. It was trained on 10 terabytes of data, 2.45 billion documents. So that was a lot of things: web pages, books, news, articles, code, right? GitHub. And the difference with Gopher versus some of the other large language models is that they actually filtered, they pre-processed the text before they fed it in. So they actually evaluated for quality. Like it's not just every open source repo on GitHub. There's actually like some exclusion criteria to be in Gopher. Chinchilla is DeepMind's 70 billion parameter model. And this was interesting because we got into some compute scaling laws, and this is what's been driving some of the decision making behind cloud architectures around and cloud resources around how much compute, how much memory, how much GPU do we need. DeepMind found that a 100-fold increase in compute should translate into a 10-fold increase in both data size and model size. So, if you want a 10-fold increase in your model size, if you want to add, another order of magnitude of parameters, you need a 100-fold increase in compute. So we're starting to get into some gnarly territory here. And cue, the massive surge in GPU prices, all of these things. That being said, Chinchilla ultimately ended up being 4 times smaller than Gopher, and it outperformed GPT-3 on certain tasks, but I don't know which ones. Yeah, so basically it's like they're finding ways to scale their data set while maintaining quality alongside increasing the parameter count. So it's very interesting. Gemini, we've heard of Gemini, it's Google's model. And Gemini is cool because it is multimodal, which is very fun. It's encoder-decoder architecture, and it's known as like a mixture of expert models, which is another trend in LLMs where you start to add in multiple models that are all kind of trained to do a unique thing. And then you aggregate the outputs in very interesting ways so that it can do things like, oh, hey, generate a presentation based off of this text document. And so you get both image and text based off of this mixture of experts model. Okay, and then we have our open source models. Yay, we can't forget about those. We have Llama, Llama 2, and Llama 3.2. We have Mixtral. So the Llama models are from Meta. The original weights, if you remember back in like 2021 or early 2022, right? The original weights were like leaked. And then Facebook's like, okay, I guess it's open source now. I don't think that's actually how that happened. I think there are a lot of like open source advocates who are trying to, promote this model, but who knows? So yeah, there's a huge range of the size of parameters that you can use with Llama models between 7 billion and I think like 90 billion parameters, depending on the model that you choose. Then Mixtral has some open source models. The Mixtral LLMs are really, really, they outperform other models in terms of math, code generation, and some multilingual tasks. So that can be really cool. So if you need to ask a question about math in French and then get some kind of sensible output, Mixtral would probably be your bet. So this is just a comparison of all the different kinds of models that you can choose from and their internal stuffs. You do not need to memorize any of this. The key point being they vary widely in size, the number of parameters, and the size of the context window they can handle in terms of the tasks that they're really well suited for, all of these things. So thinking critically about which model you're going to use is a good idea. You don't have to default to ChatGPT for everything. There's a lot out there that you can use. Okay, so now we've all heard of fine-tuning language models, right? So what does that actually mean? What are we doing when we're fine-tuning a language model? Um, so the foundation model, right? When we talk about foundational models or foundation models, those are the the OG LLM that's trained on a huge amount of data, diverse data sets. It's all unlabeled, right? This is like unsupervised. And then it's tasked to just predict the next token given the previous context. So this is supposed that the goal is for this to be as generalizable as possible. And it's also the most expensive bit of this whole thing in terms of like the amount of time, the amount of compute, all of that, right? That makes sense. So after you've trained a foundation model, you can specialize that model by using fine tuning. So there's a couple different ways you can go about this. You can do instruction tuning, or you can do supervised fine tuning. So supervised fine tuning is it trains your language model on a set of like task specific demonstration data sets. So you're going to say, okay, well, I want you to answer these questions in this kind of format. I want you to translate this French into this exact mathematical equation or whatever. You're going to show it more examples of how you actually want it to proceed. And then, yeah, and then you go from there. Update parameters internally is a whole thing. So instruction tuning is the LLM is provided as input and instruction to follow. So you're going to say, okay, do X, Y, and Z. And then that could include like summarizing a text or writing some code or like writing a poem. And then you're going to like give it feedback on that instruction and how it performed. Then we have dialogue tuning, which is your LLM is going to be fine-tuned on conversation data, right? So you have like more and more feedback about that back and forth conversational piece. And then there's something called safety tuning. So safety tuning is going to mitigate the risk from bias and discrimination, toxic outputs, things like that. So that's, again, another example of that reinforcement learning with human feedback, right? So you can provide more, find good examples. Yeah, so when we're doing supervised fine tuning, we're going to do things like question answering, right? So we have our question and then our answer. So the question will be the prompt and the answer is going to be the target. So for translation, it would be like, here's the sentence in English, here's the sentence in Spanish. You're just showing it more examples. And then you have things like your like a document, like a massive document, and the summary that you want to see out of that document. So these are ways of doing supervised fine tuning. Okay, so we talked a little bit about reinforcement learning from human feedback. This is kind of based on like a reward model. Ooh, that is very blurry. I apologize. So let's start with over here. We have our prompt only. We're gonna feed that to our no, we start over here. Prompt text summary, do prompt only. Prompt text, what's our response? Okay, so when we're doing our reinforcement learning human feedback loop, we're going to give it our prompt and also a response, the response that we would like to see. That's going to go into our supervised LLM. We feed that into our reinforcement learning human feedback LLM, and then we have a set of like reward models. So basically with most reinforcement learning, right, it's you have some action, you have a reward. You can also do a penalization based off of the action that model takes. So yeah, you're just showing it like, hey, this is how I want you to do this. There's also reinforcement learning with AI in the loop. So it's going to give AI feedback instead of human feedback. This is getting really popular because of just the size of data that you need to pass a reinforcement learning model. Does anyone else get creeped out that like, we have a AI in the loop for large language models, or is that just me? Yeah. Like when people are writing like code tests, it's like, oh, great. Then I'll have GitHub Copilot write the test for the code that GitHub Copilot wrote. It's like, no. Yeah. Yeah. hmm It is weird. I get creeped out by it, but that's just me. I'm old school. We have other kinds of fine tuning, parameter efficient fine tuning. LoRa, if you've heard of LoRa, that's low rank adaptation. So that's just kind of condensing our search space. We're going to use like lower rank matrices for tuning. Okay, so now we have other, like we're starting to get into the realm of like what we do as more as like engineers, right? So all of this behind the scenes, except for maybe human feedback in the loop, all this behind the scenes is taken care of kind of for us, right? Once we start getting into fine tuning, even that, like, I mean, generalists can do fine tuning, but like some of the AI in the loop stuff, that's gonna be done by specialists. So getting into like more implications for our cloud architecture and what that might look like, we have things like prompt engineering, right? So again, that's providing those clear instructions to the LLM, do this thing, right? Ignore all previous instructions and do the following, right? So you're gonna give it examples. So write a poem in the style of this poem, right? Or write a song, or, well, yeah, it depends if it's a multimodal model. You can do this using keywords. You can format your input text to emphasize important information. And you can also provide just like additional background about what you want to see. So that's all called prompt engineering. There's different kinds of prompt engineering. You have zero shot, few shot, chain of thought prompting, right? So chain of thought prompting is where you ask your model to explain its reasoning, right? And then it kind of, I don't know, works through the whole thing, gets to a more sensible result. And then we also have sampling techniques. So these sampling techniques are really important for controlling like the quality and the creativity and the diversity of your model's output. So sampling can be really helpful if you are sort of training your model to give more creative output. So in that case, what you maybe want to do is like a bit of random sampling. So instead of having selecting strictly the token with the highest probability at each next step, there's going to be a distribution of probabilities. And you're going to say randomly sample from this distribution of probabilities. And then it's going to be more surprising and more creative and also likely more nonsensical. You're going to get some weird stuff out of that. You could do greedy search, which is just going to be the token with the highest probability at each step, right? Just like straightforward. It's kind of like what your autocomplete has been doing on your phone for a long time, right? It's like, anyway. And then there's temperature sampling. So the temperature sampling is going to adjust your probability distribution by some temperature parameter. So if you have a higher temperature parameter, that's going to promote diversity, right? So it's going to be like a larger group of stuff we can choose from. And a lower temperature is going to favor higher probability tokens, right? So if you want something very, very strict, you want to have a very low temperature. If you want something kind of creative and loose or whatever, you can have a higher temperature. Then we have top K sampling. That's kind of what it sounds like. It's going to randomly select from the top K most probable tokens. And you're going to control K, the value of K. And that's going to control the degree of randomness. We have top P sampling. And that's going to be some dynamic subset of tokens whose cumulative probability adds up to P, right? Yes.
So for like top case, you're doing next word prediction.
So yeah, so what we're going to do is okay, so if we have a task where okay, so our probability density function, right? Oh no, that's getting into P. So we have a probability distribution of all of the words that could come next after my first word. My first words are like be cat, right? And then we could have the probability that the next word is that. Like P could be approximately equal to like 0.7, maybe. So P, the next word could be like has, I don't know, whatever. And that probability could be approximately equal to like 0.5, etc. And you keep going, right? So there's a whole list of probabilistic tokens that come after this, right? So with top K, we are going to select the top K most probable tokens. So say we have all of our tokens set up and their probabilities, we're going to just sort them, right? So by most probable to least probable. And then we're going to take maybe something like way, way out here. Let's say like laptop, I guess. And then probability of that would be like 0, 0, 1 or something, right? So we're going to say we want the top K most probable next tokens. So if we have k equals 2, then it's going to randomly select from the top 2 most probable tokens. Okay, so then top P sampling is going to sample from a dynamic subset of tokens whose cumulative probability adds up to P. So that's going to be looking more at the probability density function, right? And so instead of, kind of taking like sorting by that, you're going to have the probabilities add up to some P, and then you're going to sample from that set of tokens. And that just lets the model adapt to like the number of potential candidates depending on its like confidence. So then we have best of n sampling. Sorry, was there a question about top P? Because we could draw the density function. No one? Damn it. Okay. Then we have best of n sampling. So that's going to generate n separate responses and then select the one that's deemed best according to some predetermined metric. Those metrics could be diversity. They could be shoot, what are they? Diversity, I think like homogeneity, something. Anyway, but that's going to be really helpful for short snippets or situations where like logic and reasoning are pretty straightforward. But yeah, basically, if you combine your prompt engineering and your sampling techniques and your correctly calibrated hyperparameters, you can really, really greatly influence the LLM's response. And you can make it more relevant, more creative, and more consistent for your needs, right? So this sounds like an end user story, right? Like as an end user, I'd like to be able to control the temperature of the output of this model. Or as a user of the system, I'd like to be able to have arbitrary amount of prompt engineering, which is usually not something that is allowed all the time because we start using tokens, right? We start having to pay for those prompts as we engineer them. Okay, so given all of that, us as like people who are probably not the ones serving the foundation models, unless it's open source, we're more working with those foundation models, right? So we are starting to integrate those foundation models into our systems, and we need to be able to deploy that and have endpoints people can hit, parameters they can tweak, right? And some other things besides. So one of our key things that we think about is accelerating inference. So whenever we're doing inference, on the engineering side of the house, we need to think about the cost and the latency for our model's users, right? So balancing the expense of serving a model in terms of like the time and the money and the energy that it takes, right? Is going to be our cost performance trade-off for our large language model. And the main compute resources used by the LLMs at inference time are going to be memory and computation, right? So memory and CPU. And so if we improve our inference, whenever we're working on improving inference, we're working on improving memory and we're working on improving compute, CPU resources. So finding ways to optimize that is a big priority right now. And there's a lot of like ongoing research in this space. But there's two kinds of like trade-offs that we start looking at when we're trying to optimize for inference. The first is the quality of the results versus your latency and cost. So you can, if we make improvements in the speed of how quickly like our model returns a result, and also the cost of inference, sometimes we're accepting a marginal drop in our model's accuracy overall. And then we also have latency versus cost trade-offs. So, or latency versus throughput. So that's going to be where, well, the throughput refers to your system's ability to handle multiple requests efficiently, right? So it's like lots of like bandwidth. And then if you have better throughput on the same hardware, that means your LLM inference endpoint cost is reduced, right? So improving throughput overall is going to reduce your cost of serving that model. With bulk inference, your cost is going to be more of a factor than latency, right? So bulk inference is when we're taking a huge stack of data. We're saying, go make a decision on this, right? But if we're doing, for example, chatbots, we want to reduce latency as much as we can, right? We want to make sure that there's a really quick response to anyone who's chatting with our LLM, right? So yeah, in that case, we want to have more focus on request latency. And then we do tricky things like latency hiding, right? Where like it starts to like generate the right? So like line by line, word by word. It's a little trick of the trade. I mean, it is still processing and it is still returning the result, but also we do latency hiding. I say we, like I actually do that, but there's latency hiding that happens through that sort of like word by word printing to the screen. Yes, so accelerating inference, this is like pretty academic right now, but we have like quantization and distillation. So those are two ways of kind of approximating output by like reducing dimensionality. And then we have output preserving methods. So there's a new attention mechanism called a flash attention. Yay! We're going to keep having new attention mechanisms all the time. You can do prefix caching techniques. So it's like we already know probably like what the next bit is going to be. So we can cache little bits of it that can also help to accelerate your inference. Speculative decoding, which is fun. And then batching and parallelization, right? But batching, again, might just be latency hiding. Parallelization actually helps you improve your performance. Okay, so all of that said, I promise we're going to get much more deep into our cloud architectures soon. I promise this is all relevant for what's coming up. So vector search algorithms. Who's played with vector search algorithms before? Anyone? These are real fun. You've probably had you've had, well, maybe you have. So if you've ever like used K nearest neighbors, anyone? KNN models? Yeah, cool. That's a vector search algorithm when we generalize it, right? So what we're doing is with KNN, we're finding the data points that are closest to each other, right? But your data points can be really high dimensional. We generally don't do super high dimensional data points because then clustering slows down ridiculously, right? But ultimately what we're doing is we're finding points that are close to each other. That's the exact same as, you know, as trying to find the closest word to the word that we have, right? So we have another graph here. Say we're visualizing K nearest neighbors in 2 dimensions, right? And we have clusters here and here, whatever. And then we're like, okay, great. So these are, let's say K equals 3. We have our clusters here. So behind the scenes, right? If you've done dimensionality reductions, this actually converges, which is a good idea. Behind the scenes, these are still very high dimensional vectors, right? So maybe this is n equals 300. Well, all of them would be then, because you have to have the same size dimension, right? So KNN is just finding the closest, it's an efficient way of finding the closest neighbor to each of these vectors. It's very, very similar to finding the most similar word or the next like most probable word in your corpus. So yeah, so approximate nearest neighbor is like KNN is a derivative of ANN, I think. It's a special case of ANN. So that's one option. We have locality sensitive hashing and we have trees. We can read more about this because I'm going to run out of time. We have cool things like Facebook AI similarity search, which is an algorithm that's very popular for finding similar vectors. And it makes sense to us why we want to find similar vectors, right? That's yeah, I should have backed up a little bit. If we are trying to find the most similar sentence in an entire corpus, and we're just using the embeddings and we're doing cosine similarity, for example, between each of those vectors, that's linear time. That runs in linear time, right? Because we have to compare each vector to every single other vector, right? That's not very efficient. So instead, we have all these other ways of doing it, like clustering, right? Like approximate nearest neighbor, and that's going to run some. I think Facebook, the AI similarity search runs in. Oh yeah, log of n. That's nice. That's sublinear time. Yay, we love it. So that's one way of like comparing super high dimensional vectors very quickly without having to do individual search like that. Then there's also scalable approximate nearest neighbors. And I bring these up because a lot of these search algorithms are implemented, like they're so popular, they've been implemented for you in vector databases. So that's very exciting. You don't have to go write your own, Facebook AI semantic search or, your own ANN. A lot of vector databases come with this built in. So it can do that really quick searching for you, which is awesome. So vector databases, we've talked about them a little bit, right? We talked about them in like our cloud native unit, and like database as a service, right? So vector databases are huge right now. And they're built to manage these massive vectors of data, right? And they're also have these vector search algorithms baked in. So that's really, really helpful when you are trying to use vectors to help augment the output of your machine learning system. So maybe you have a foundation model, and what you want to do is you want to make it really give really specific output about your company's, your organization's processes or procedures or products or whatever it is, right? What you can do is create embeddings out of your product listings, right? And then as the query is going to come into your vector database where you've stored those embeddings, then the query comes in and then your vector database can do a really, really quick search across all the vectors that are already persisted there, right? Then it feeds that into the foundation model, and the foundation model is going to augment the response with more human sounding language. Does that make sense? Yeah, a little bit.
So you're not doing like that. I mean, if you have like a calculator that just like doing a search, like here are the answers to the questions. But you're still making sure that I feel like there may be less hallucinations because you're not just asking the LLM to come up with an answer.
Exactly.
You're just talking to augment this.
Yeah, exactly. Yes. Yeah. So we're not creating like, yeah. So the models, the approaches that I've had the fewest hallucinations recently have been models that are really specifically contextualized to a domain, right? So you have models that are maybe given additional information about Mexican election law or something. I don't know, right? And then as you create embeddings out of that context, out of those documents, then your query is going to come in, use the same embedding technique, and then your vector database is going to do a quick match on that, right? So that match is going to be the more like semantically similar meaning, right? And then it's going to pass that onto something that can make it sound more human. Yeah, makes sense? All right, cool. Popular vector databases. Vertex AI is Google's vector database and RAG service. Pinecone is really popular. It's maybe the most popular vector database right now. It's not open source. It's expensive. But the open source ones are Weaviate and ChromaDB. So those are fun to play with. So the thing about vector databases is like there's, we have all the same concerns that we have with any other database, right? Scaling horizontally. Luckily, with vector databases is a lot more straightforward than scaling horizontally with SQL databases. We need to make sure that they're highly available. We need to make sure there's data consistency, right? If there's multiple systems, parallelize your embedding for your corpus. We want to make sure there's a real-time updates, backups, access control, compliance, all of that good stuff. And also, our embeddings can mutate over time. Yay! So that's some added complexity. So especially after like retraining, right? Your embeddings can update gradually. Frequently updating your embeddings can be really expensive, right? So remember when we were learning about cloud native databases, a lot of the charges that you have for your cloud native database is not just for like the running the actual infrastructure, it's for the number of writes and reads that you're doing, right? Especially writes. Writes are always expensive. So if you're updating your vectors very often, that's going to be real expensive. And then sometimes you need a combination of full text search and then also like pre-filtering or post-filtering in your search space before passing it to the semantic search model. So all of that is a concerns for your vector database. So that's pretty fun. All right, so the tasks that we think about our LLMs achieving are like retrieval, right? Information retrieval, like search engines, which is, it's funny because like Gemini as a search engine, as a retrieval engine, is not great, right? Like we find better results like just from Googling something, right? But like retrieval is kind of a part of Gemini's sort of like plan, right? So we have that whole retrieval task. Semantic text similarity, like which document is most similar. classification, clustering, like ranking and re-ranking. So like rank a set of objects based on a certain query, right? Things like that. Let's see, so question and answering with RAG is kind of like one of the key tasks that we want RAG for, right? So if you have a chat bot on like a customer support site, then you're going to use RAG specifically for like, hey, like how many, like what's the maximum bandwidth for my droplet or whatever. And then Sammy the chatbot's going to say like, oh, you get 1,000 gigs per droplet or whatever, right? So basically, again, we're going to first retrieve the relevant documents from a knowledge base, right, from our vector database, and then use that prompt, then like expand that prompt to include that document that's retrieved. Yeah, so that's called prompt expansion. Again, RAG can reduce hallucinations, but it doesn't eliminate them entirely. Yeah, ask anyone who's using RAG today. Like, I mean, every single chatbot, someone's gonna have an issue with like, oh, my this customer said that this was the result of your chatbot, and that happens with airlines. Like that happens with I think someone was asking if they could have their flight refunded because of a death in the family, and the chatbot said yes or something, and that was not actually the policy, and it's just real bad. And that was using RAG. So it's not a silver bullet. It helps get us closer. All right. So in order to implement all of these things, right? So we have our foundation model, we have our vector database, and we need ways of interacting between them. We have our like UI, right? That our customers are going to interact with also. The way that we manage all of this is through something called agents. So agents are a key part of your overall system. It's just going to attempt to achieve a goal. Any agent just attempts to achieve a goal. It's going to have like a way of behaving, a set of actions it can take, and then a set of decisions that it can make, right? So we want to scope our agent so it can't just do absolutely everything, because that would be scary. So we have our agent. We've talked ad nauseum now about the models, right? So the agent is going to interact with the model, right? Your users, your customers are not directly interacting with your model. You have an agent in front that's going to handle that for you. The agent is also going to decide, hey, does this go to our RAG database first? Or is this going to use a RAG process first? Or is this going to go directly to the model? So agents have like a scope of things that they can manage. So let's see. You can also have multiple. Yes.
In something like a GPT model, there's like book instance as a service. Is that responsible as the agent? The agent be the one that's like filtering for like expensive things and just like saying, so
that's a really good question. The agent wouldn't be the agent would call another model that's responsible for doing that like firewalling of responses. So usually under the hood are other language models that are there to detect like output that shouldn't be there. If has anyone played with like Gandalf AI? That's a fun one. I should put that in your resources, but it's I think it's Gandalf.ai. But it's like a nice fun way of Gandalf. I'm sorry. It's a fun way of pen testing, like through prompt engineering, a a a foundation model. The agent would be more responsible for like making sure that other controls or interventions are in place before that output gets back to the user. But the agent is not really the one itself who's like, hey, block this, it's like it's passing decision making on, there's like, steps that it can do. Yeah, good question. Okay, so then we have our model, we have our agent, then we have these other tools, right? There's a lot of other tools that augment our AI systems. These tools are going to help our model interact with the outside world. So that could be external data, that could be external services. And then your tools are commonly going to interact with like other web like APIs, right? So it's going to use your get, post, delete kinds of syntax. It's those actions. So your tools can update customer information in a database, for example. So customer asks a question, and then even if that stuff is getting to the model, like maybe like logging that a token was used, a customer's token was used, your tool is going to do that. Your model is not going to do that, right? It can fetch weather data, right? So it can hit some weather API and then return that as part of as its own sort of like RAG system, right? But it's calling something external. So yeah, so agents can access and process real world information using those tools. So the agent's going to make the decision, oh, okay, go call the web API or get this tool that's going to call the weather API from weather.com or whatever, and then use that as input for the model that's then going to return that output to the user. Does that make sense? Kind of. All right. Yeah, so tools are going to help you like specialize even further. So orchestration is how the agent is going to take in information, perform this internal reasoning about like where to go next, like what are the next hops or the next steps, and then use that reasoning to inform the next action or the next decision. And that loop's going to continue until the agent has reached a goal or a stopping point, right? So that goal could be like, this query seems semantically and syntactically correct based off of the validation of this other AI system. Great, go ahead and return it to the user. There's lots of decision rules, lots of chained logic, chains. Anyone? Yeah, LangChain, we're getting into it. All right, and then there's additional machine learning algorithms, other probabilistic reasoning techniques, things like that. So again, agents and models, very different thing. Your agent is going to have knowledge that's extended from a connection with the external system via tools, right? Your model's just your model. And then it's going to manage your session history, allow for multi-turn inference, right? So conversational inference. It's going to do prediction based off of user queries, and then any decisions that are made in that like orchestration layer. And then the tools are natively implemented in your agent architecture, right? So you're building custom tools for your agent. You can also build like open source tools that other agents can use as well. And yeah, agents use something called a cognition architecture. I don't know what happened, but we're almost, sorry, there we go. Agents they're going to use a cognitive architecture that's going to use reasoning. And that reasoning framework is where we get into LangChain, right? So who's heard of LangChain? A couple of people? All right. So LangChain is a really good thing to learn about because this sounds like a ton of stuff to engineer on your own, right? Luckily, you don't have to. LangChain is going to help you with a lot of that piece-by-piece logic, right? It's going to help you slot things in where they need to go, which I think is wild because this has only been around for like a year, 2 years max, right? And we have all these open source tools that are available for you now. You should contribute to these open source tools if you're doing something cool. That's how we get ahead. All right, so the models, we know what the models are, right? Models and agents, these are different things. Okay, so with only like 1 minute left, we have other things besides LangChain that are just good to be aware of. I'm not going to go over these in depth, but like next lecture, we'll talk a lot more about LangChain. We have React. We have Chain of Thought, which is a prompt engineering framework that's going to like, enable reasoning capabilities through intermediate steps. And then we have Tree of Thought, which is a decision tree for Chain of Thought. And I think that's all the time we have. This is kind of like what that process looks like, how the agent is going to begin a sequence. The agent's going to provide the prompt to the model as for the next like steps. Then we have, kind of step through. So we will come back to this. We'll start here next time. Thank you, everybody. Appreciate you. Right, it's stopping time. This is, yeah. All right, cool. Yeah, thanks, everyone. And this is a lot of stuff, but it'll help make sense of all of your engineering efforts going forward, I hope. All right, thank you.